In this lesson, we're going to discuss logarithms. So what is a logarithm? A logarithm is more or less an exponent. So to show you that, we're going to go back and forth from logarithmic form to exponential form so you can see how they relate. So essentially log base b of y equaling x can be rewritten as b to the x power equaling y in exponential form. So essentially, the log of the base is the answer, and on the other side of the equal sign is really the exponent. So let's see how we do this going back and forth from exponential form to logarithmic form and vice versa. So the first example, it says rewrite as a logarithmic equation 5 squared equals 25. So the first thing I'm going to do is write the word log. The subscript is going to be the base. So what's being raised to a power, and that's 5. And remember, on the other side of the equal sign is the power in which 5 is raised. And of course, 25 would be the answer. So again, 5 is raised to the second power to give us 25, or some people read it 2 is the power in which 5, our base, must be raised to give us 25. So again, let's write it now in exponential form from logarithmic form. So log base 2 of 1/16 equals -4. So my base is 2. Remember, the exponent's on the other side of the equal sign. And the answer is 1/16. So -4 is the power in which 2 must be raised to give us 1/16. Okay, now let's talk about something base e. So when we have log base e of x, that's the same as the natural log of x. That's not an I in front of the N, that's an L. So it's the natural log of x is the same thing as log base e. So again, let's go ahead and change from exponential form to logarithmic, and from logarithmic form to exponential form. So again, we're rewriting as in logarithmic form. So I'm going to write the word log. My base in this case is base e. My exponent is y. My answer to raising e to the y power is 7. Now keep in mind, log base e is the same thing as the natural log. So our answer could be written as the natural log of 7 equals y. Okay, so let's look at the next one. So here we have the natural log of x equaling 5. So we know what the base is of the natural log, but so that you can see it, remember again that the natural log is the same thing as log base e. So the first thing that we're going to do is rewrite this as log base e of x equals 5. So again, my base is e. The power in which e is raised is 5. And the answer of raising e to the 5th power is x. Now let's evaluate a couple of logarithms, and we're going to discuss 2 different ways to do this. So one, we're going to try to express the answer, the 1/36 in the first example, as 6 raised to some power. So in this case, we have the log base 6 of 1 over 36 equals some value. So what we're looking for is the exponent. Remember, that's what the logarithm is. So we're looking for 6 raised to some power is going to give us 136. So now you can rewrite 36 as 6 to the second power. Since it's in the denominator, remember, that would be a negative exponent. So this would be 6 to the x would equal 6 to the negative second power. And so our answer, so we're saying 6 raised to what power gives us 6 to the negative second? Well, of course, if the bases are the same, for them to be equal, the exponents have to be the same. So that means x would have to be -2. So in other words, 6 to the negative second power should equal 136, and it does. Because remember, the negative exponent tells you to take the reciprocal. So we have 6 to the second power, which is 36, and the reciprocal of that is 1 over 36. Okay, let's try it with the second one. So here we have log base 4 of 64. So again, what are we looking for? We're looking for 4 raised to some power. And remember, what we're looking for is the power that would give us 64. So what we're going to try to do in this case is rewrite 64 as 4 raised to some power. So we know that 4 raised to the third power is 64. So since our bases are the same, in order for the equation to be true, the exponents have to be equal. So that means that x would have to equal 3. So think about it. 4 to the third power has to equal 64 in order for this to be a correct answer, and we know that 4 to the third power is 64. So our answer checks. Now the question is what if you can't make them the same base? Then we use something called the change of base formula. And I'm going to just do it with the second one, although you can do it with both of them, and you can do it any time with this. So again, given log base 4 of 64, if we're looking for the exponent of 4 that gives you 64, then another way to do it is using the change of base formula. And in the change of base formula, we can find our answer by taking the log of 64 over the log of 4. So if you put that in your calculator, you'll get the answer to be 3. Let's try one that's a little bit different. Let's say we were doing log base 2 of 7. Well, there is no value that we know that 2 can be raised to give us 7. So we're going to use that change of base formula. So on your calculator, you're going to put the log of 7 over the log of 2. So again, in your calculator, you're going to put the log of 7 over the log of 2, and that gives you 2.807. So that means, again, that 2 raised to the 2.807, and remember, this is rounded, should equal 7. So the change of base formula, or if you can write them as having the same base, either method will work. Now let's talk about graphing logarithms. So remember when we talked about exponential functions. So what did we say when we had an exponential function? And I'm going to take exponential growth problem, we know that the domain is all real numbers. And we know that the range goes from 0 to infinity. Well, with logarithmic functions, a logarithm is an inverse of an exponential function. So when we look at a logarithmic function, remember x and y switch places, so the domain and range switch places. So the range of an exponential function is going to be the domain of a logarithmic function, and the range of a logarithmic function is going to be the domain of an exponential function. Okay, so now when you look at this graph, it says translate. So we're going back to our transformations or our translations. So we're given log base 2 of x, and that's what you see graphed there. So again, let's talk about those points that we talked about with exponential functions. With exponential functions, we said that with every graph before translations, that the graph would pass through 0, 1, and 1, and whatever the base is. So when we talk about base 2, if that were the case, it would pass through the point 0, 1, and 1, and since the base is 2, base 2. So that's just using this as an example. Okay, so again, when we look at the log of having base 2, remember they're inverses. So that means in logarithms, it's going to pass through the point 1, 0 because x and y switch places, and then 2, 1. Okay, again, exponential having base 2 and log base 2. Okay, so when we look at this graph again, we have something called a vertical asymptote. Notice our graph doesn't go to the left of the y-axis. So there's really an imaginary line that comes down our y-axis that the graph approaches as it goes down, but never touches or crosses. Notice this graph goes through the point 1, 0, and it also goes through the point 2, 1, just like we said. Okay, so now with the transformation, we have x minus 4, which means we're going to have a horizontal shift because of values being added or subtracted directly to the x of 4 units to the right. Remember, it's opposite. So if it's minus, it's going to be to the right. And since we have plus 3, we're going to have a vertical shift. So our graph's going to shift up 3 units. So we're going to take our points. 1, 0. So if we move to the right 4 units, 1 plus 4 is 5. And we're going to move up 3 units. So 0 plus 3 is 3. So again, with the other point that we know, 2, 1, if we move to the right 4, that becomes positive 6. And if we move up 3, 1 plus 3 is 4. So we have points at 5, 3, and 6, 4. Okay, also, since we have a shift to the right of 4, our asymptote moves over 4 as well. So our graph won't move to the left or touch x equaling 4. So our graph's going to look like this. So again, in a logarithmic function, Our parent function has a vertical asymptote at x equals 0. And if we're moving our graph, shifting our graph left or right, our asymptote moves with it. Okay, so let's look at the next one. Here it says graph the function g of x equals log base 2 of x minus 1. So let's look at the parent function again. So remember, we have a vertical asymptote. That means our graph doesn't touch or go to the left of x equals 0. And remember, for all logarithmic functions, it will go through the point 1, 0. And whatever the base is, in this case 2, 1. So our parent function would look like this before the shift. Now what's happening to our graph? Our graph is shifting to the right 1. So all of our points shift to the right 1. So that means our asymptote shifts over as well. So I'm going to draw a separate graph. So at 1, we have our vertical asymptote. That's that imaginary line. So originally, remember, our graph goes to the point 1, 0, and this one 2, 1, because our base is 2. Now if our graph shifts to the right 1, because of this being x minus 1, it will go through the point 2, 0, because we're adding 1 to our x values, and 3, 1. So it goes to the point 2, 0, and 3, 1. So now, again, we have that same shape. It approaches our asymptote, but never crosses. Now when we look at our domain and range. So remember, originally our domain are those values greater than 0. Since we shifted our graph over to the right 1, our domain changes. And what we can do is we can set the x minus 1 greater than 0, and we'll do that each time to determine our domain. So now we're going to add 1 to both of these. So x would have to be greater than 1 is our domain. So remember, if we're writing it in an interval notation, our domain goes from 1 to infinity. And if you look, our graph continues forever to the right. So that's our domain. Our range. What's the lowest point on the graph? The graph continues indefinitely downwards. So that's negative infinity. And how high up does my graph go? To positive infinity. So the only thing that changes is our domain, and that's dependent on what our horizontal shift would be. Now, properties of logarithms. Remember, logarithms relate the same as exponents. So let's talk about the logarithm of a product. So look what happens. When we have log base b of m times n, that can be rewritten as log base b of m plus log base b of n. Why? Look at your rules of exponents. Whenever you're multiplying like bases, what do you do with the exponents? You add them. So when we're talking about product in both exponents and logarithms, we're defining or determining addition. Quotient rule, the logarithm of a quotient. When we have log base b of something divided by another quantity, we can rewrite that as a subtraction problem. Log base b of m minus log base b of n. Why? Look at our rules of exponents. Whenever we divide like bases, we subtract the exponents. Last the logarithm of a power. So if we have log base b of, in this case, m raised to the n power, what happens is that exponent goes in front of the logarithm, and then we would have n log base b of m. And again, look at y. Whenever we're using the power rule of exponents, when we raise a power to a power, we multiply. So again, whenever you're learning these properties, keep in mind what we're talking about and how do they relate to the rules of exponents. So here's a few examples. For the product property, log of 9x, again, product means we're multiplying two quantities together. Remember, whenever we're multiplying like bases, we add the exponent, so this would be addition. So it'd be the log of 9 plus the log of x. For the quotient rule, again, whenever we're dividing like bases, we subtract exponents. So here we have log of 3 over x equals log of 3 minus log of x. And then the power rule, log of x cubed. Remember, the exponent in this case, which is 3, would go in front of the logarithm. So that's the same as 3 times the log of x. And again, using the similar power property of exponents. Whenever we raise a power to a power, we multiply the exponents. Okay, so we're going to use these in a second, but I want to also remind you that the square root of x is the same thing as x raised to the 1/2 power. Just like if we had the cube root of x, that would equal x to the 1/3 power. So we're going to use that concept as well as these properties of logarithms. So now here, we have used the properties of logarithms to expand the following expressions. So here we have the log of the quantity, the square root of y z to the 5th over just x cubed. So we have a lot of properties that we're going to deal with in this case. So the first thing that I'm going to do is go ahead and use the quotient rule. So the quotient rule says when we're dividing, and you can see that we're dividing the square root of y z to the 5th by x cubed. So remember, the quotient rule means subtraction. So I have the log of the square root of y z to the 5th minus, why is it minus? Because the x to the 3rd is in the denominator, the log of x to the 3rd. I can rewrite this as the log and rewrite these as the square root of y times the square root of z to the 5th minus log of x to the 3rd. Now, since I'm multiplying the square root of y and the square root of z to the 5th, I can use the product property. So this can become the log of the square root of y plus the log of the square root of z to the 5th minus the log of x to the 3rd. Now remember what we just said. We can change it from radical form to an exponent. So this could be the log of y to the 1/2 power plus the log of z to the 5/2 power. Why is it 5? Because it's raised to the 5th power minus the log of x cubed. Now our last step is to use that power property. So remember, if we have an exponent, that would go in front of our logarithm. So this would become 1/2 the log of y plus 5/2 the log of z minus, now this 3 would go in front, 3 log of x. Okay, so that was expanding. Now let's do a process called condensing. Here you're given a logarithm that's been expanded. What was the original problem beforehand? So what we're going to do is work backwards, and we're going to always start by reversing the power rule. So this 1/3, since it's in front of the logarithm, is really the exponent of w. So here we'd have log base 4 of w to the 1/3 power. Plus, since the 3 is in front of the logarithm for y, remember that would be the exponent of y. So here we'd have log base 4 of y cubed minus log base 4 of x. Okay, now keep in mind what a fraction as an exponent means. That means it's a radicals. So this is going to change to log base 4 of the cube root, because our denominator is 3, of w plus log base 4 of y cubed minus log base 4 of x. Now, after we've reversed the power property and we've taken care of changing it from a rational exponent to a radical, now we can deal with the product and the quotient. Since these first two are being added together, that means we're using the product property. So this can become log base 4. Now I'm going to put the y to the third first, so it doesn't confuse you to think that it goes under the radical sign, because it doesn't. So it'd be y to the third times the cube root of w minus log base 4 of x. Okay, so now, since I have a minus, that means I use the quotient rule here. So I'd have log base 4. Now in my numerator would be that y to the third cube root of w, and in my denominator would be the x. Okay, so that's what we call condensing, or writing it as a single logarithm.